these leads and then generate some score for these leads. Okay, then from lead, then you convert into an opportunity. Once you know that, okay, this lead or prospect has some interest in buying your company's product, and then from opportunity to customer, actually, it's quite a long process. Typically, it takes like 3 to 6 months. And if you are dealing with federal government, so it takes 1 or 2 years. That's also normal, okay? And then that's why, like, here at Clary, we're trying to leverage some of this machine learning and deep learning technology here, so to apply to this sales management and forecast. So there would be 2 problems which we will cover tonight. One is opportunity scoring, so which is essentially trying to identify which deals are at risk, how likely this deal can be closed by the end of the quarter. And then the other problem is projection. So that's more like aggregation of these individual deals. You're trying, as a manager or executive, the number one problem I want to answer is, okay, how much revenue I can make by the end of a quarter. And if you are working in a public company, if the number is off by probably 2%, or if more than that, like off by 5 or 10%, you're probably in big trouble. So that's why, like, there's a lot of efforts going on trying to make sure your projection is accurate. So next, I would hand over to our data scientist, Xin. She would cover some of the technology used here for opportunity scoring. So.
Hello everyone, my name is Xin Xu. Right now I'm a data scientist working in Clary. So as Dr. Lei Tang just mentioned, today I will walk you through some of our recent exploration on how we apply deep learning to solve the opportunity scoring problem. Okay, so we hope that we can share some of our findings and hope that will be helpful to your own problem. Okay, let's get started. So like in the last few years, with the development of like big data, like some hardware like GPU, TPU, and also cloud computing, deep learning has a lot of very exciting applications in the industry. So for example, for this one, this is the object recognition, which is the key technology for self-driving, and also like for machine translation and speech recognition. And also like this is the most very famous AlphaGo, which is a big win for deep learning. But actually, the concept of deep learning is not something new. It has been there for many years. It's nothing but to apply some deep neural network to solve some problem. Here, deep neural network it's like a neural network with more than one hidden layer. So the graph on the left is the main component for the neural network. So what it does here is like it has some input like F1, X2, X3, and we apply some weights W1, W2, W3. And the key component here is like applying some nonlinear function to the summation of W multiply X here. The nonlinear function can be sigmoid or ReLU or like tanh function, and then we get the output. A typical neural network has an architecture like this. So it is composed of like input layer, and also it composed of this layer is called hidden layer. Basically, it's trying to get more abstracted feature from the input layer. And also we have the up layer here. Yeah, if you have more complicated function that you want to capture here, you can make the network wider and deeper. So it even can be like thousands of layers or thousands of neurons in each layers. Okay, so you can see that for this type of neural network, basically there is no loop in there. So all the thread is going from the input directly to the output. So for this type of neural network, we call it feed-forward neural network. However, in many cases, your input is more like a sequential data. But for the feed-forward neural network, the basic assumption is that you have, like, the data should be more like independent of each other. So that's the reason that we introduced the recurrent neural network here. Say, for example, if you are doing a machine translation, your output is not only related to the current input, but it's also related to the word before the current word. So that's the reason we have this. And the graph on the left actually has, you see that the difference here is there is a loop there. And the graph on the right actually is the same, but it's a different representation. we unfold the graph over the timeline here. One very well-known issue with the RNN is that it has a vanishing gradient issue and the exploding gradient issue. And it is not very good at capture long-term dependency. Although in theory that you can use RNN to capture the dependency as long as possible, but it's not just doing the right thing. So some people introduce a new type of recurrent neural network. So here it is called long short-term memory, or sometimes we call it LSTM for short. The only difference here is that instead of using some nonlinear function like ReLU or sigmoid function or like just a step function, here we replace that with LSTM unit. So you can see that here in the middle, the main reason that it can capture the long-term dependency is that it has this more like a highway for the cell state, so that the history data can directly go through. So that's the reason that it can solve the issue. It has a notion of it has a notion of gate. So basically, it contains 3 gates here. The first one is called the forget gate, which is I showed it up here. It basically captures how much information we want to get from the past. So also we have the input gate, which you can see here is capture like how much information we want to grab from the current observation. And the overall flow for the input gate and forget gate is that you have the cell state CT minus 1, which is the cell state from last step. We multiply this value with f of t, which is the output of forget gate. So you see that if the forget gate is basically the sigmoid function, which have the value range from 0 to 1. If it is 0, then that means all the past history won't pass through because we have a product here, right? If it is 1, then all the information from the past will get through. And then we like concatenate that value with the value we get from the input gate. So this forms the new cell state, which is C of t here. Okay, and then we have the third gate, which is the output gate. What it's doing here is like it controls how much information actually we want to output in this step. So that's a like high-level idea for this LSTM. Okay, so after the brief introduction, let's talk about what is the problems that we want to solve here. So the problem is we call it opportunity scoring. I think that most of people sitting here don't have the domain knowledge, so I will just briefly introduce what is opportunity. It's basically it's a sale or a pending deal that you want to track here. Say its corresponding history, its associated history is more like a sequence of the event that is associated with that opportunity. Say assumes that this is a timeline for opportunity, and so opportunity is usually in the form of like somebody change certain fields from the old state to the. Can you hear me? So from the old state to a new state at a certain time. So the first event happens to this event is the first meeting, and then after a while we see that it is doing like POC, which is the proof of concept here, and also after a while it has maybe the sales rep specify there's some competitors, so there's some competition there, and then it's backing off and receive the purchase order and the legal issue. Finally, it will end up with close won or close lost. So this is what like typical opportunity look like. Just to give you a brief idea, like for each opportunity, we have roughly like 200 to 400 fields to track. But for usually for each arc, we probably they probably maintain like 50 to 100 among those fields to be quite actively updated. And those fields can be like can be either numerical or categorical, can be date, currency, or it can also be some text there. Okay, so then after we introduce what is opportunity, then what is opportunity scoring? Say assumes that you have opportunity right now. It's not closed yet. which means it is not reaching the final stage, no final decision yet. So for those type of opportunity, we call it open opportunity. So what we want to do is that we want to predict if this opportunity will be close to lost or close to won. So we use CM score or opportunity score to predict how likely an opportunity will be closed as one. So in production, we have the opportunity score showing here, which is a score ranging from 0 to 1. If it is 0, then that means we think with no possibility that this deal can be closed. If the score shows 100, we think this will be closed for sure. Also, we provide certain type of explanation for these deals, for this score. So what it did is like, it tells us why this opportunity, we think that this opportunity can be closed, and also what are the main reasons that this score got increased or decreased in a certain time. We actually provide different type of scores in our production, but today, since I don't have much time, so I will only focus on just one type of score that we provide in the production, which is the probability of 1 by end of quarter. I think from the methodology perspective, they kind of using this quite similar techniques, but I will mainly focus on this today. Okay, so now let's talk about how we do the thing we want. First, we need to generate the data we have. We need. We actually have tried two methods to generate the data. The first one is that, first let's recall that because we are trying to use the deep learning, especially for the LSTM method, kind of the input should be like a sequential data. Okay, so the first method we use here is a step-based method, which basically every 7 days we collected one observation. So for example, for this case, this is the first observation. We see that at this particular time, the stage name is S1, the forecast field is F1, and price is 1,000. So there's no competitor specified at this moment, and the time is also not specified. The close date is specified as January the 30th here. And after 7 days, we have the second observation, and we continue this process to generate a sequence of the observations. So we consider here is just as one sample. And the target label for this opportunity, if it is close 1, then we say that is target label 1. Otherwise, it will be it will be 0. Okay. However, there's one issue we find with this method, because for some of the opportunities, so if, for example, they are not quite actively updating the deals, say maybe for a very long period of time, they have everything remains the same, then we probably end up like repeated observations there. And also for those deals that maybe they quite actively updating each fields, and within 7 days they already change a lot of fields there, but we only get one observation. This is for this case, this method probably is not the right way to do the sampling. So we try to figure out a second method to collect the sample data, which is a event-based method. So we only collect the samples when some events happens here. Say, for example, for this case, we have this same observation, and the second labels we generate here is only when the second events happen, and then we collect a sequence of the samples. Again, this is just one sample. All these observations will be just among one samples, because we need to use sequential data for training purpose. And then, again, for this case, it has label 1. Now let's talk about what are the models that we use here. We basically try different variations of LSTM. So the first model we tried is just a vanilla LSTM. We put the sequential data in, and only in the last step we predict if these deals will be lost or what. Another one variation for the LSTM is that we can do LSTM with mean averaging. because recall that in last method, we only predict in the last step. But maybe in the middle, we already observe some of the quite indicative signals there. Say, for example, in the second step, feature at k-1 there, we already see they update the field as purchase order, but later they got changed. So for that method, it's probably not quite able to capture that. So we try to average all the input in each step. So this is a second method we tried. And okay.
Just 2 slides back. So you have irregular sequence data, and you don't know the number of events which will belong to one sequence.
A number of the events.
So this one rectangle you're showing is
Yeah.
one sequence, right?
This one?
It's one sequence.
This one is one observation. So as a
That's all those events put together as one.
yeah, right.
So because they're all different in quantity, then how do you fight them?
So you mean like the observation is different for different observation for different sample? Is that what you mean?
Yeah, then how do you fight that into the LSTM? Because then you need a window size.
Yeah, right. Actually, for this case, we truncate all the sequence. Say like we truncate like 14 observations for each sample.
Okay, so
Yeah.
14.
Yeah, but in theory, actually, it can be like a very varying length. But like for this case, because it's easier for training, so we basically truncate that into the same length. Yeah. Okay, and the third method we have here is LSTM with dropout. So dropout is a very common methodology that we use if sometimes when we deal with relatively small data sets. If you train a very complicated model, it is very likely to be overfitting. So we can use this dropout method. Basically, you can random drop some of the output there. So we attach a dropout layer to the output of like the hidden layer. Okay. Just to prevent the overfitting issue. Also, we tried LSTM with feature embedding because as I just mentioned, like we have roughly 200 to 400 views for the CM data. It's like only among them just only like 50 to 100 are actively updating. So that means the metrics or the features are quite sparse. So in that case, we don't want to train the model use a very high-dimensional feature vectors. So we would like to first convert it into a low-dimensional vector before we do the training. So here we attach another layer to basically is to multiply the weight here to make it like a lower dimension matrix and train it together with the other parts. Okay. Also, we tried stacked LSTM because if like you want to capture more complicated nonlinear function, so this will allows you, say, second layer allows you to have more abstracted features like derived from the first input layer, like LSTM layer. And also the last variation that we tried here is LSTM with raw features. So instead of just have the LSTM network here, we also directly connected a linear function of the input to the final prediction result. The reason we do that is in two folds. The first one is that so first we basically try some traditional machine learning models like linear regression, which basically only use the current status for the prediction. We observe that for this type of model, it already gives us pretty good result. So we think that the last step probably contains the most important information here. So we basically want to more emphasize the last step information. And also another reason is that this is more domain specific because like we have some fields which is not history tracking. We call it non-history tracking fields. So for those fields, we don't know what will happen in history. We only know the current status. So we want to also leverage the information from those fields. So we have this raw features input here. So this is a this is the last variation we tried here for opportunity scoring. Okay, so after we train the model, we also need to generate the test data. Actually, we missed some variation here. So if you recall, like for the more general method, it's more like you have a very huge data set. You probably want to randomly divide the data into like training data and the test data, maybe like 70% of the training data, 30% of test data. But for this case, we are more like, we have a cutoff date. So before the cutoff date, we do the training. We use the data for the training. Say we use the opportunities which closed before the cutoff date for the training purpose. But we only use the opportunities after the cutoff date as the test data. So the reason we did this is because we basically want to try to mimic what is really happening in the system. Because what we can do, the data we can use to train the model is that what we observed from the past. But what we really do the work or do the opportunity scoring in the production is we are using the later time data. So, and during this process, there might be a lot of things change. Say maybe the business process change and some other things got changed. We want to see under these cases, maybe everything is not so ideal. Under this case, if we could get a good result out of this model. So here are some of the methods that we can compare. So we have the probability model, logistic regression, random forest, and gradient boosted classifier. I will not go into too much details about that. We are kind of using the first one and the fourth one here in the production. Just refresh some of the memory. Like for this model, the training data actually have to be independent. We cannot use the sequential data for those models. So in order to train those models, we can only leverage the current observation for the training purpose. Yeah. So here are some of the comparison results. You see that this is just one organization. We have to implement this over all the organization, but I think it's probably not allowed to show like our data here. Okay, so I would just take one example here, an anonymous organization. I think for other orgs, the number is kind of different, but the trend is quite similar with this. Okay, so for the traditional machine learning models, like probability model, LCM, like gradient boosted classifier, random forest, or linear regression, we observe that usually the gradient boosted classifier is like performing the best. And for the LSTM-based method or variation of the LSTM-based method, we observe that averagely they are better than a linear regression or random forest, but it's not getting too much better. The best model we tried, best model over all the test data we have is like the event-based model and over LSTM, but here we also have the embedding included in the model. It is kind of having the best result here. It is kind of 1% increase for this org. And also like we try to plot out the score distribution. Seems that for all the models, they kind of give out the similar result. The score distribution are kind of similar. I think that's quite match our intuition here. And also, like here is one example for the opportunity, how the opportunity scoring evolve over the timeline. Say in the very beginning, like you see we have some status like on November the 18th. The close date is specified like as February 20th, and it is in stage 2, and the forecast category is the pipeline. Before the next event happens, actually there is no events there. But since we are predicting the probability that a deal will close by the end of quarter, so that means they are kind of, this opportunity is kind of approaching the end of the quarter. So the score, although there's no event happens, but the score is still decreasing. Okay, and okay, after on like January the 8th, so we see there is some change. The close date is like changed to it's changed to April the 28th. It's kind of pushed back. So we think, okay, at least the model think, this will be indicator that this deal probably cannot be closed. So the CM score have a sudden dip. And also, like, quite shorter time, they update the close date to be like February the 22nd. And the stage is also updated to stage 7 committed. Forecast category is the expected. So we think, okay, it seems that this deal got like pulled back, and the stage got like kind of pushed, like moving forward. So it's quite match our intuition that suddenly it will have a very good score, say here kind of like 90 something. So we think very likely that this deal will be closed. Some quick takeaway here is that, so first you can see that deep learning is actually doing the thing we want. It's actually giving us good result, but it is not as good as we expect. So just for, okay, any question?
Yeah, you just showed AUC, but you did not show accuracy or other measures.
Oh yeah, so here we only show AUC here.
But you did look at other measures accuracy.
We look at some other accuracy, like how many like data can be correctly classified, but we didn't show it here. Yeah, I think just the what?
Could you repeat the question?
Sorry, I didn't quite hear you. Can you be? Well, measure AUC.
20% or 30% of the data set?
Oh, actually, this is for the test data. So the question is that when I measure the AUC, it's like 20% of data, or like for 30%, something like that. Because like for each opportunity, we are training one model, right? And we have the test data. We have a cutoff date, and between the cutoff date and the current date, we kind of have some opportunities there that we want to measure if we can correctly classify those deals. So we use all those test data for this AUC calculation. What is embedding for? Okay, so this is one variation that we have the embedding. Basically, is to make a how do you say high dimensional vector into like a low dimensional vector.
I know word embedding. This is word embedding?
Not in word embedding. It's like, for example, here we have a bunch of features. As I said, we have like 200 to 400 fields, right? But most of the fields are not actively being used. It's only like 50 to maybe 100 fields got actively updated. So if we use all the fields, it's okay, but it seems then we will end up like very high dimensional calculation. I think it's not quite expensive. So in this case, we introduce embedding. So before we train the model, we try to make the high dimensional vector into a like much lower dimensional vector for the training purpose. Yeah.
How do you train embedding?
So here we. No. It's yeah. I think we actually discussed there are several ways. Like you can probably do some PCA just to find the main component. But here in this case, we because this is just a very initial exploration we have so far, so we haven't tested all the other cases yet. So for this case, we just more like multiply some vector, multiply some matrix with the input vector. And then, like, we train this together with the LSTM. Yeah.
Also, you mentioned that the model is trained for each customer.
Yeah.
Which is, the question is, this is because you don't want to, customers are not allowing to use, or you don't see see a value or you tested there is no value, to train model first on the lots of customers and then train it later for a specific customer. It seems like you could have taken advantage of multiple customers. At least say embedding probably is not specific to individual customers.
Yeah, I think your suggestion is a good way. But right now we only train individual models, and later I will talk about this because right now we are still in the we are still in the offline exploration phase. Yeah, we have some method in the production, and we are trying to implement this into the production. But at the same time, okay. So do you mind? Like maybe I can share with you some of the takeaway away here, and we can talk about this later. Yeah.
Excuse me. I just want to add one comment to the question. The question is why we didn't train the model using the data across all different orgs. So actually, you raise the first issue is that because we are dealing with financial data, it's quite sensitive. So most customers are not happy to share the numbers or whatever patterns with others. Then on the other hand, we did try to see whether there's any pattern, like you can do some transfer learning or share some patterns, but there are quite some complexity. For example, even though normally this opportunity will go through different stages, but like one org, they can define 30 different stages. The other org probably just goes through 5 stages. So when you take this input as some features, you don't know how to map these features, right? So and also like normally in this opportunity, they have their own custom fields. So different org, different vertical, they have very different pattern. It's very difficult to map this kind of field and values to each other. So that's why it's kind of remain a kind of quite challenging to trying to do this transfer learning for these different orgs. Actually, I believe later she will talk about looking at the text, which we feel that probably can be shared across different orgs. Yeah.
So here are some takeaways that we have through the exploration. So the first thing, as I just mentioned, like we see that deep learning is doing the right, looks like it is doing the right thing, but it's in many cases it's not giving us much better performance compared with the traditional method. We think that there might be 2 reasons for this. The first one is, so for some of the organizations that we have, as we just said, so we basically train one model for each organization. So for small orgs, it's prone to the overfitting issue. So in that case, the deep learning model is probably not the right way to go. And also in our applications, we already see that even if you use some traditional machine learning model like linear regression, like gradient classifier, it's already gives us great results, which this model basically just train a model based on the current observation. So that means maybe the data in the past, in the last day or in today is already good enough to provide enough information for the training purpose. Okay, maybe the history doesn't help much in this case. Also, if you compare the complexity, like time complexity, deep learning is also is not also not comparable with traditional machine learning model. So, for example, I observed that for one organization, like when we use just gradient bootstrap classifier, it's kind of like 10 minutes or 10 to 20 minutes is enough. But for deep learning, it's probably takes up to like 2 hours for training with like 10 epoch of data. Okay, so I think that when we choose the right model for the prediction, we always want to take into consideration the trade-off between more complicated model but with a little bit more accurate result, or versus the simple model but with less slightly worse result. So this is something that we need to take into consideration.
It's a little surprising that you haven't said the word economic or money yet. In most business cases, it's very important to be able to track the economics and the money and the finances of your potential clients and their client. And it's almost surprising that you're not putting in data that measures that.
So David,
experienced businessmen. They track the economics of their customers, and so on deeply.
We actually don't track that. That's not the data we have here. So we, most of...
Is that an opportunity perhaps to add?
Maybe, yeah, I think maybe in the future we will consider that. But right now we don't have that data, yeah. Also, like instead of here, I want to mention that instead of just picking one model for to serve all the purpose, say we also do the model selection, because for a different model, maybe they are good at capture certain type of behavior. So we kind of do a model selection for to always pick the best model for each organization. So we basically train different models there. Also, like another thing we always mention about deep learning is the interpretability. So it is usually very hard to interpret why this model is giving us this kind of result. So, but in industry, actually, we need to provide the customer some explanations. So that's also an issue that we need to deal with. Okay, so that's our exploration on the opportunity scoring. Another thing that we kind of question.
The size of training sample size you have. So what would be the sample size and what would reduce minimal?
Sample size? Actually, it depends, because we have different organizations. Like there are some very large organizations like HP, or we also have some small organizations at which, like, they only have three reps. Yeah, of course for those like orgs, we will not train LSTM model. But in terms of what is the size, I probably cannot tell you here. But kind of we usually train on very large organizations. Yeah.
And then your label is just basically deal close one.
Yeah, close one lost. Just a one or zero. Right, right.
I didn't see your deep neural network architecture, like in terms of the LSTM unit and whatnot.
Which one?
So, I guess what I'm trying to say is, like, if you tune your LSTM DNN, you might find more performance with neural network.
You mean the performance for AOC?
So you don't show your neural network architecture here.
You mean like
Show this genetic
this one?
how LSTM works, but
This one? These are the neural networks that we train. The kind of, we are using the variation of LSTM.
so just one layer of LSTM, that's it.
Also, we try stacked LSTM, or with different variation, like we add the embedding or add the dropout, tune the parameters. That's the variations we try. Yeah.
So my experience with LSTM is that it's actually suited for solving a large data problem.
Yeah,
You need
right.
a lot of training data.
Right.
But today's talk is about small data. So what's the connection?
So what is the, so you mean like,
Small data.
so I think here that today, I don't know, what do you, maybe from the introduction of the talk, they say maybe small data. I'm not, I'm, how to say, like, as I first said, so for us, we don't have like maybe tons of data, that large of data, like what Google have or Facebook have. What we have is, compared with their data, we have to say that our data is more like a mid-sized data, but it's not small. It's not, maybe it's not too small, because otherwise we cannot use the deep learning, use the deep learning for the training purpose. It will go overfitting. And also, like for some of the cases, as I said, for small orgs, maybe not so small orgs, we kind of observe the overfitting issue. So when we after we train the model, we have the test data is not quite, for the test data, it's not doing right. But if we add the dropout kind of mechanisms to prevent the overfitting issue, then it's getting much better. So that means maybe for this type of data, it's probably kind of small for STM. So that's my understanding, yeah.
So I think especially here we are dealing with sequential data. So each sequence you can have probably 50 different updates. So it really depends how you view the data. If you just count the number of opportunities, that's not many. Could be like hundreds, thousands, or like tens of like thousands. But if you look at the number of events associated with each sequence, then that could multiply by like 100. So that could you could end up with lots of like updates. But then there's also other issues that most time the update is probably you only update like a couple fields. So essentially each update is highly, highly correlated with each other. So there's you did get some information, but that's not much. So that's why we want to explore to see, okay, whether deep learning can be applied here. Well, we were not sure whether deep learning really work, right? So that's why we want to share some findings here.
Did you try to solve the correlation issue by just differencing it? Because otherwise you have the same vector repeated, and the model could be confused which one is really important. But you highlighted that the last vector is actually informative. So you could actually make it stick by differencing backward and essentially accounting only for the changes.
Can you repeat the question? Sorry, I don't quite
So
capture
for
it.
the history, can you just difference the history and essentially train on fields, not on the vector? Since most fields will leave those fields at the very end.
That's not the case. Almost all the fields got quite frequently updated. So, for example, like if you look at the stage name, we call it stage. Like it's probably in the very beginning it is stage 1, and then later becomes stage 2 and move on to stage 3. And it's probably if the field is not doing right, and they move it back to stage 2, and then go back forwards, go back and forth, like something like that. Also, like for example, for some price. It's probably like in the beginning they specify like 1,000, but they make some deals with the company and they like kind of give them a 90% of discount later, something. So all the fields that they actually using actually got quite frequently like updated. Yeah. So I see. Yeah. Yeah. Not the diff, but more like the second way is we only generate our observation when there's some new event happen.
Okay. Another question is you have a lot of customers, right? And you have a lot of SLCM variation.
Yeah.
For each customer, each model configuration, do you have like tuned individually, like a number of LCM units, all those things? Or you have a crossover? Like
Yeah, that's cross line. The horizontal line is just the one unit, but it's recurrent.
I mean, how many units you have, like, for example,
You mean like for the how many observations I have for each for?
For example, your deep neural network architecture,
Uh-huh.
how many STM units you have?
So this part is
These questions are getting a little detailed. Could we kind of hold the questions until the end and actually finish up the talk and then ask the questions? And for questions that are at that level of detail, it might be best just to ask them to the speakers after the talk is complete.
okay. Also, there's another area that we can leverage the power of deep learning, which is we use the word-to-vec for the text analysis. Because in some of the fields associated with the deal, there are some text fields. Say, also, like, actually, we have various sources of text data, such as the next step fields, which is just one particular field. And also, we have the email associated with one particular deal. Maybe sales constantly exchange some emails with the customer. And also, they have some meeting notes, maybe some random words about what is happening and what will be happening in the next. And sorry. OK. And we observed that for those text data, actually, it contains a lot of strong indicative signals. Say, if we see the word like sign, order, final, purchase, most likely this deal will be closed in the end. So we also want to leverage the information from the text data. So how can we improve the CRM score? By leveraging those text data. OK, so first thing you want to do is that you want to represent the text data. The easiest way, no doubt, is the one-hot representation. Say you have a very large vector, you have very large dimensional vector. You use each entry to represent each word. Say, for example, for apple, you use the first entry to represent this word, and it is 1. All the other entries will be just a 0. Okay, so but for this kind of representation, there are some issues. So the first main issue is that it's not easy to capture the similarities between, it is not the right way to capture the similarities between different words. Say, if you look at, say, angles or the similarities between apple and banana, you say it would be just a 0. And also, like for apple and dog, it's also 0. But you would more expect that apple is more closer to banana, and it's farther away from dog. But the one-hot representation is not good at capturing that. Another main issue that forbade that like keep us from using it is that if we use one-hot representation, the dimensionality of the data will be huge. Basically, the size will be equal to the vocabulary size, which is usually larger than 10K. Okay, so we try to figure out another way. Say we use the distributional dissimilarity-based representations. The high-level idea is that we want to use some low-dimensional dense vector to capture the meaning of the word. So say so for example, say like this derived from the concept that if you have 2 words, if the surrounding words for these 2 words are almost the same, so we can kind of guess that these 2 words have the similar meanings. So in this method, in this kind of representation, people usually use 2 models, very popular models. The first one is the skip-grab model. The second one is a continuous back-and-words model. Since we are using the skip-grab model, I will only introduce that in today's talk. But the only difference between these, they're quite similar actually. The difference between these 2 models are like for skip-grab model, basically we use the central word to predict the surrounding word. But for the continuous back-and-words model, we are trying to use the surrounding words to predict the central word. That's the only difference. So I will only talk about the skip-grab model here. Say you have a sentence. You have a sentence here. The quick brown fox jumps over the lazy dog. Then we have a window to capture what is the. Oh. Oh, okay, sorry. We have a window here, like we have a maybe window for size 5, and in the beginning, the window is in the very beginning of the in the sentence. Then we get a training sample like they and quick. So here they is the central word, quick is the surrounding word, and also we get another pair like they is a central word and brown is like surrounding word, and then we shift the window 1 step. Say we got a quick as a central word this time, and also they and brown and fox. These are the surrounding words we want to capture, and also like for this very long sentence or paragraph, you can generate tons of training samples. Okay, so here is the architecture for the skip-grab model. So the input here is one-hot representation or one-hot encoding. So this is the central word you put here. And then we have the hidden layer. So here the hidden layer is pretty simple. It even don't have the nonlinear function. It's just a linear neurons here. And then the output of the hidden layer will go to the up layer. So since we are predicting the probability here, so we use the softmax classifier. And so here what you want to predict is the surrounding word, right? So this is the one-hot representation for the surrounding word. When you calculate the cost function, basically you calculate the cross entropy between this output of the network and the surrounding word one-hot representations. Okay, but there is one issue here. if you look at that, if you read their original paper, say, you see that output, as I said, the issue associated with the one-hot representation is that the dimensionality is like a huge. You probably end up like more than 10,000 entries here. But among those 10,000 entries here, there are only one, but all the other entries are 0. So they propose a method which is called negative sampling. Basically, they only sample a very limited number of the 0 and also keep that 1. Say they probably choose 5 to 10 zeros there, and for the training purpose. So when you calculate the cost function, you only updated the weights that associated with those few 0 and the only 1. So that will make the network more effective. Otherwise, you have to update all the weights here. That will be very little improvement in every step. So different from the other models, neural networks, which you usually want to predict what is the final output, maybe the final probability or classifications. But here, what you want to predict from, what you want to get from the skipgram is actually the weight, which is the output of the hidden layer. Because you want to train this model and get the low-dimensional vector to represent the input word. Okay. Okay, so here is some of our analysis. So now we kind of aggregate all the text data and train this model. And we find, you see, like, we try to find out the similar words for PO. So PO, which means purchase order in our domain. And you see the most similar words for purchase order is order, like processing, some orders placed, rebuilt, kind of match our intuition. And also like losing, the most similar words is the behind, and the fighting, totally, risk, stalling, concern, lost, and also for upside and one. So it looks like the word-to-vec is doing the right thing. It helps us to find the most similar words there. So how can we leverage the information from the text for to help further improve the CRM score or opportunity score? So here is the overall flow. So first we have the opportunities ready, and then on one hand we generate the features, which we first exclude all the text features, all the other features just like what we did in the last step, and also we collect on the other thread. We collected all the next step text within the last 15 days as of today. So the reason that we collected the text data within 15 days instead of just look at the current data is because for this fields, it's not so, how do you say, it's not so, it's kind of sparse. The data is kind of sparse. It's not as dense as we expect. So maybe they don't actively updating this field. So we kind of aggregating more data from history. And then we, after we get the text, we want to get the vector representation of the text. We have a pre-trained word-to-vector model that we use this model to predict what is the low-dimensional vector for each word, and we get the average of the text fields here. And then now we have a low-dimensional vector output of this part. And then we simply consider that low-dimensional vector as some features, and put it together with all the other features and put it into the classifier for the training purpose. And this is how we generate the final score. Okay. Okay. So this is for opportunity scoring, and I will leave the rest to Dr. Lei Tang for projection.
All right. Okay. So what is projection? And I think if you look at any company, they have this quarterly revenue report. So, but typically, they need to set some goal for the next quarter, say how much revenue they can achieve. So that's essentially doing projection. But for us, we are actually trying to do projection not just for the whole org, but also like for each team, each region, and also each salesperson. So you have to, essentially you consider there's a hierarchy, then they can just like go through this hierarchy trying to get the number for each person, each role. And also it could be possible they have different opportunity types. So like say you want to separate new business from renewals, then you want to project separately. So essentially there's different ways to slice the data, but then you need to come up with some projection, okay? So when you look at a projection, naturally you would relate this to some time series because there could be some trend. Normally startups could grow like say this year compared with last year, increase like the growth is like 2,000%. And then there are also some seasonality. It really depends on the vertical. So sometimes like the fourth quarter tends to be tough for certain orgs, right? And then also there could be some other variations. Like for example, if you're working on CRM, then normally like there's some big events, like some marketing event going on that could naturally lead to some sales change as well. And then of course there's some random fluctuation, and more likely there's some outliers. So we did see that one sales rep put 1 million deal as 1 billion, which totally blow off the numbers. And so that could happen. And then here is just give a, sorry, I have to hide those numbers, just too sensitive. And then this is just one module in our product. It basically gives you a sense like, as you can see here, the past 4 quarters, then you can see like how many deals were at the best case, at commit or different stages. And then among those open deals, and then how many actually got closed by the end of the quarter. So this can give a view, like compare with same time last year or same time past quarter. What's the conversion rate for my deals? And then if you look at current quarter, then here we're trying to give you some projection, right? So in the end, we're trying to, based on past quarter patterns, trying to compute a projection for you. And similarly, you can do that, look at the longer, like along with the timeline. So we're trying to compute the projection basically each day. So here we're showing every week. And then we're also showing these different pipelines, like how many deals. The bottom green bar is actually how many deals has been closed when you enter into the quarter. So this you can almost like go back, look at the past quarter, and see how the projection evolve every day. Okay, so that's kind of the projection, but then when you look at the problem, actually it's very, very challenging. So if you're working on time series, you hope for there's some strong pattern. So ideally we want to see, all these pipeline grow, how they decline near the end of the quarter. But the reality looks like this. Most orgs look like this. So there could be sudden jump, sudden dip, and then a lot of variation going on. So, and also there are a lot of like business process change. So when we talk to our customers, almost any of these customers, they would say, don't trust data beyond 2 years because they changed the VP of sales, because we went through some acquisition, the whole sales process got changed, right? So, so that's why like you have very, very limited data in a sense. If you go back for 2 years, consider seasonality, you only have 8 quarters. Okay, so that's why like there are a lot of tricky things going on here. And also there are some bias towards quota. So each salesperson, typically they have some quota number. If they achieve the quota, they can get a higher commission, right? So as you can see, there's something, even though it's pretty smooth, there's something like say at that point, somehow they are closing too fast and then they want to slow down because they have enough time and they can achieve their quota. So that naturally happen. And also there's certain orgs actually, even though they close, they try to push these closed deals to next quarter so that the next quarter would not suffer too much pressure, right? So this all happens in these different organizations. And then another important issue here is that you might think this projection is simply the aggregation of individual opportunities. That's not the case, because normally you want to have some number like at the beginning of the quarter, but when we look at the when you were at the beginning of the quarter, roughly 30 to 50% of deals were not even in the system yet. So if you're just aggregating all the existing deals, you only probably can get like a small portion of the revenue number. So in a sense, you have to figure out a way to predict how many new deals would be coming. So this might be newly created, and also there's some deals might put in from future quarters. So that all happens. As you can see here, right? So when you are at here, so you kind of like, okay, 50% deal were not even in the system. But some quarters, okay, only 20% deals were not in the system. So there are quite a lot of variations going on, right? So so there's one method we're trying here is trying to predict the end of quarter revenue. Then you're trying to use opportunity scores to aggregate all these existing pipelines. So as you can see here, there's a score which is indicates how likely this deal can be closed by the end of the quarter. On the other hand, you also need to predict what are the likely revenue for this particular deal, because the deal size could change, right? So based on their pattern, you're trying to see, okay, if this deal can be closed, what are the likely deal size, right? It could be possible that like at the beginning of the quarter, many of these deals, they don't even specify the deal size, but you don't want to assign a $0 value to that deal, right? So that's why you have some way to figure out what are the likely deal size. Is the deal size going to increase, decrease, right? So what's the ratio look like? And then you also have a separate bucket is for the newly created deals. So that you have to look at different patterns. For example, how large is sales team? And then if you get the quota information, you can even include the quota information as one of the input as well. And then essentially trying to throw all the possible variables and figure out what are the likely, how many new deals they would be created. But on the other hand, we noticed that for many of these arcs, if you, this is just one method. It's like kind of these different arcs exhibit different patterns. So that's why we end up have to try other approaches as well, like standard time series analysis. And also if you look at the close pattern, it's also like each day becomes a sequence. You can also apply some kind of LSTM to do that, right? And also there, we also tried some non-parametric method. It's actually by just looking at past, like same time past quarter, what's the conversion rate? And then you can simply apply to current quarter. And it's hard to say which one would be the eventual winner. So we basically try all these different patterns. There's always some org have new patterns, and you have to come up with some new method to deal with that. So as a quick summary for today's talk, essentially for opportunity scoring and for projection, our system is end up eventually goes wider and wider because you have these different patterns. Deep learning is become just one method or one component in the system. It won't address all the issues. Actually, in the system, we have regression, we have clustering, we have classification. All these are coming together. So that's why like we tend to have model selection for this both opportunity scoring, and then let the model selection process decide which ones works the best. And another interesting, I would say interesting findings that when I deal with these financial data like sales data, I was really amazed by how they organize the system. And then so different orgs have very different patterns. And then so that's why kind of in a sense we have to go wider rather than deeper in our domain. Okay, so that's pretty much today's talk, and we're welcome for questions.
So when you ask questions, please take a moment to sort of stand up and introduce who you are and where you're from, if you have some institutional affiliation. And also, if you raise your hand and I can come by and bring you the microphone, then it's easy for everyone to hear your questions and not just the answers. And of course, that's good for our viewers at home as well, who'd like to be able to hear the questions and answers together. And I guess Dr. Li or Dr. Xin, you can direct questions to each of them individually or to them as a panel or whatever suits you best. So who's first?
Hi, I'm Bo. I have been working on deep learning for a couple of years. So my question actually is about the projection for time series data prediction. So your slides was a little bit short on details. So could you tell me a little bit more? In the end, what's the system like? Do you have multiple time series predictors working together, or is that one particular method performs better than others? Thank you.
Okay, so you can consider this more like a multiple time series rather than just a closed revenue number, because you can group all these open deals by different stages. And then essentially, like say, if at a later stage, when they approach the end of quarter, that tends to close. But like for all other open deals, they would slip. So you essentially look at these different deals, like deals at different stage, then you look at how they change, fluctuate each day, then you end up with multiple time series. But for our prediction, we only care about end of quarter revenue number, right? So you can consider each timestamp there's an input, but then there are multiple like deals at different stages, and then you can model each day as one like kind of each day becomes one step, and then what you care is by the end of quarter how much revenue I will end, right?
Anyone else?
I'm Go Morihara. I work for a Japanese company, and I'm a software developer. And from that perspective, I have two totally different questions. One is about testing. You said that you were using the whole data before the cutoff date as the training, and the left is for the training. But how long did you have those training times? I mean that I see that. I believe that this sales kind of things is quite seasonal, and if you come to the end of the year or maybe month, that's the score should be high, because those customers are running out of time and want to close desperately or something like that. But if you test like that, it sounds not a test to me. It could be a real big bias for that. Why did you choose that kind of way to test?
Okay, so the question was, why do we choose a cutoff date? And before the cutoff date, we use all the data for training and then use the remaining time for testing. So first, I think that basically explains how do you do the prediction for one day. Essentially, what you can do is go back to last quarter, right? So you can do this every day. That's essential because we can constantly refresh the model when new data comes. So you can essentially basically set every day as a cutoff date and trying to measure the performance. Then you can get an average, like across the whole quarter, what's the performance each day. And then based on that, you can do different type of aggregation, because certain orgs, they only care about, like say, the last 2 weeks near the end of quarter. That matters most. At the beginning, probably, okay, it's fine that that's not so accurate. And also, like at the beginning, probably many deals are still at the early stage, so that's naturally, most of them deals would be considered have very low score, naturally, right? And also, concerning the other point, you mentioned about this seasonality of the sales process. So when we train the model, we try to include the number of days left until the end of quarter. That's one of the most important features there, okay? And the number of business days until the end quarter, that also should be considered, because especially during holiday season, the number of business days do matter, right? So that natural capture this timing and seasonality effect.
So my second question is,
Well, let's try to keep it moving. I mean, circle back.
Okay, I'm Pat Ransel. I started working in artificial neural networks back when they called them that, back in the mid-'80s. Took some time off doing some other things, back in it now. On your bag of words architecture, you mentioned that you use softmax instead of sigmoid. I agree that softmax would be better than a sigmoid, but even that will tend to saturate, and you'll end up having low to zero gradients on most of your outputs often. So have you tried just using a linear output on the final layer for training, because that'll preserve your gradients better?
Xin.
Actually, we didn't try that, but I think that's a good suggestion. Maybe we should try it later.
Name is Subrata. I work for a startup. So, time series, I actually did not get what is the y-axis for the time series and what the x-axis is obviously time, right? So, that's my first question. Second question is, this data is probably from multiple industries, right? So, I mean, how can you find commonality between multiple industries? I have a third question, but I'm going to skip it now.
Okay, so the first question was what's my y-axis? That's the revenue number, so that's why I have to hide it. Okay, so actually, from these patterns, if you have data, you can figure out which org that could be, just based on the scale of the number. And then, excuse me, what's the second question? Okay, so the second question is like, we are dealing with organizations from different verticals, and then what's the commonality? Or is there any commonality? I have to say, most likely, they don't have much things share in common. And then it really depends on the org. Even within the same org, we see different opportunity type can exhibit very different pattern. Like renewals, it's 80% renewal you can close, but new business, it's not the case. And then if you're dealing with different clients, for example, you're dealing with federal government, that has its own seasonality, okay? And the sales process could take, like say, 1 or 2 years, that's normal, okay? But if you're dealing with like large enterprise or mid-market, so all these teams, they are dealing with different clients, they end up with have different sales pattern. So here today, we don't have much time to talk about, but actually there's some segmentation process going on, even within the same org, because you cannot apply the same model for the same for one org. You end up probably have to segment the deals within the same org into different types and trying to come up with a model for different types.
Okay, we have time for one more question. Who's got one? Okay.
In epidemiology, it's quite traditional to use analog data. In this case, maybe there's something like that that's easily available that would be very relevant, which is if you group you're looking at companies as individuals, but in fact, in many cases, they or their customers, in fact, are part of industries of similar-looking businesses, and we know that often these similar-looking businesses have real strong correlations. If you added this analogy data, you have richer, more meaningful data on which to base your predictions.
I think this is probably not a question. It's more like a comment, because trying to make some analogy between different orgs, trying to identify certain patterns. Yeah, that's definitely interesting. I think a promising direction to go. But right now, I think we already have lots of issues to dealing with one org's data, like especially dealing with outliers. So that one we haven't spent much effort there. Just from another, I just want to add a comment is that from economy aspect, right? So we have a boutique data science team. There's so many directions you want to go, right? So you have to prioritize which ones are likely to yield the best business value. You cannot say, okay, today we have some GAN or some other type of like deep neural network. Okay, then we just jump in trying to deploy that in production. That won't work. If that's the case, I think we won't have the company here, right? So I think most important, we want to identify one system that really scale well and robust. Because we actually, from our experience, most time it's like all these outliers is always throwing us like sometimes throw us out of the ballpark. So and then from our side, like we're trying to automate the whole process, like for example, model selection as well, because we are not like Facebook or Google. You have like hundreds or thousands of people working on this system, right? So you have to make sure you be wise enough to spend the time and effort on the right problem, right?
All right, let's thank Dr. Lei and Dr. Xin one more time.